So this is a continuation of 1.2. So this is 1.2 B as in boy, starting on the top of page 81, finding domains of functions. Alright, so let's just read through that first couple sentences on top of page 81. When a function f, whose inputs and outputs are real numbers, is given by a formula, the domain is understood to be the set of all inputs for which the expression is defined as a real number. Okay, very, very confusing statement there, but pretty much what that says is when we have a function. So let's say our function is, and we'll look at example 8 here, let's say our function is 1 over x minus 3. And our input, we're looking for the function of 1. So 1 is our input. So what we're going to be doing here is taking this 1 and putting it in here for x. So we're inputting it in for x, and then it is going to kick out an answer when we put 1 in there for x. So let's go ahead and do that. We put 1 in there for x, we get 1 minus 3, or 1 over negative 2. So this here is a real number, and it spits out a real number. So our input is real, our output is real. So therefore, it works. F1 is considered to be defined if our answer is going to be in the same domain as our number here, which is the set of real numbers. So that's a real number, that's a real number, and we're good to go. If we look at the next example that we have there, I'll put that in red, and that would be f of 3. That equals 1 over 3 minus 3, which is equal to 1 over 0. Now, that is not defined. So therefore, since division of 0 is not defined, number 3 is not in the domain of f. It does not work for this particular function because 3 makes that function undefined. So 3 doesn't work. Okay, so let's continue on with part B of example 8. So we're looking at the function of g of x, and we're going to say that equals the square root of x plus 5. So there is our formula, and we're going to put in our input 16. So that gives us the square root of 16 plus 5 equals 4 plus 5 is 9. Okay, so since this is defined, okay, when we put in a 16 for that function, we get 9. 16 is in the domain of g. It works for this. If we were to put in, like their example here, negative 7, we get the square root of negative 7 plus 5, which, you're going to get an imaginary number, and the problem is an imaginary number is not within the set of real numbers. So this is not in the domain. Okay, so I'm sorry, the negative 7 isn't in the domain to make this possible. So the rule is that whenever you put a number in a function, and if it makes the denominator 0, or it gives you a negative radicand in an even root, so like the square root of negative 7, I mean if I had a cubed root of negative 8, that equals negative 2. That works. So that's why I say if the radicand, the number under here, is negative, and if the index is even, then it is not in the domain of a function. So if you look at example 9, f of x equals 1 over x minus 3. So the only input that will give us a 0 in the denominator is a 3. So the set of all x such that x does not equal 3 would be your domain. So what this is saying right here is x can be any number as long as it's not 3, and that'll work. Alright, if you look at B, we have g of x, and that equals the square root of 3 minus x plus 5. Okay, so when you look at what you can put in here for x, we don't want a negative exponent. So, what we have a choice of is x such that x must be smaller or equal to 3. Okay, so for example, if x were negative 4, that would be 3 plus 4, which would give you a positive number. If we had 3 minus another number less than or equal to 3, 1. 3 minus 1 is 2, the square root of 2 plus 5. Okay, so we're still dealing with real numbers. And another way to write this is, like we had done earlier, any number to negative infinity, and it can go to and include 3. So that's another way of writing. So either way, either one of these kind of depends on if they want interval notation, which is what this is, or set builder notation, which is what that is. And sometimes they may ask you to put it in one or the other. If we look back up here at the top, now that I'm thinking about it, I probably should show you that. Let's put this in interval notation. So that's going to be any number from negative infinity to 3, and from 3 to positive infinity. So that'll be like that, and that'll be that. Curved on both of them, and it will have a union sign, meaning both of them. This is our or. The number has to be greater than 3 or less than 3, as long as it is not 3. Alright, so let's continue on to look at this other example, C, and it gives us h of x, and they say that that is 3x squared minus x plus 7, and we're going to put that over x squared plus 2x minus 3. Okay, so we can substitute any real number in the numerator, not going to make any difference at all, but what we need to do, we need to take the denominator and break it down into its factors so I can find out what numbers I can use. So let's do a 3 and a 1 and a minus and a plus. Okay, so x cannot be negative 3 and it cannot be 1, because that would make this, the denominator, 0 or undefined. So you can write this as the set of all x such that x is not equal to negative 3 and x cannot be equal to 1. So there's set builder notation. If you want to do it in interval notation, it's going to be a little bit more complicated, so let me erase all this so we can make it fit. So this says that it cannot be negative 3 and it cannot be 1, but it can be all other numbers. So it can be less than negative 3 and go all the way to negative 3, but it can include negative 3. It can also go from negative 3 to 1, but not include either one of those numbers. And then it goes from 1, but can't include 1, to infinity. So this whole thing would be interval notation, and then this would be set builder notation for the same one. Okay, so this next section on page 82, it says visualizing domain and range.